Good morning, everyone. This is Class 2 of Series Level 1 Allegro CL Lisp instruction. And today we're going to be doing some programming constructs having to do with conditionals, iteration, and recursion, and certain program control structures. So now we're getting to the point where we're about to write real programs. But before we do that, there was homework, and I just wanted, this is the last homework problem, which is write a function that takes 2 required and 2 optional arguments and then prints out all the arguments supplied. Now the thing about printing out when they're optional arguments are always given a value nil. So we have 2 required arguments, x and y, and 2 optional arguments, a and b, and we print out x and we print out y because they're always there, but we only want to print out a or a and b if they were supplied. And you can't test the value of a. You can't say, well, if a is nil, then it wasn't supplied, because maybe it was supplied, but given the value nil. That's a perfectly respectable value. So you have to use the 3 element list to specify the optional argument, the name of the argument A, the initial value, which we're saying, or the default value, which is nil, and then a second symbol, which will be true or nil as a value is or is not supplied. We then test that value, and if it is true, A-P is true, that means the value is supplied for A, we print A, and if B.B is true, we print B. Notice that if A wasn't supplied, B can't be supplied, so this second test doesn't have to be run in all cases, but this is the simplest way to program it. And here we call the function 3 times with just 2 arguments. It prints them out, returns nil, which is the value of this, the last form evaluated, if BP, print B. It's also the value returned by print. Here it is with 3 arguments, which are, the first 2 at least are non-numeric. The symbol A, the string foo, and the number 2, prints them all out. And I guess I didn't give an example with 4. So I just wanted to show, that's one of the homework problems. If you have questions about any of the others, either send me an email or ask them at the end. So let's go back to the slides and see if we can get it to work here. There we go. Just some review of what we did last week. When you start Lisp, you normally, in the process of running Lisp, create a large number of objects. You create symbols, you give the symbols values, you define functions, and you may create the values that you create could be other kinds of Lisp objects, such as numbers and arrays and strings, etc., etc. And so as you work in Lisp, you're creating these objects, and as long as you have some name for the object, you can access them. You, as the user, work with a read eval print loop, which is provided, which is part of the Lisp session. It's what gives you the prompt. When you type to the prompt, what you type is read. It is then evaluated, and the result of the evaluation is printed out. And typically you work with an editor, and preferably a Lisp knowledgeable editor. Now Lisp knowledgeable, let's go back to the Allegro CL here, and here's an editor, and this is a Lisp knowledgeable editor, which means that when you are typing, and here we're defining a function that takes no arguments, you notice that when I hit return, the cursor does not go back to the beginning of the line, but is indented. There is an indenting style in writing Lisp code that allows you to read the code much more easily. And so let's say we're going to get to format later. So format T, and you will explain presently how to do these things, but at the moment I'm just showing the editor. So I'm going to hit return again, and you'll notice that now we're indented under the format. It isn't aligned with that, indicating that we're still part of the form, the call to format. And let's just call a, now in the, when you're running the IDE, if you hit Control period, it will complete the function name or give you a list of possible completions. Get universal time is a function, a predefined list function with takes no arguments, that checks the machine clock and tells you the time in universal time format, which is basically a very large integer. And so we evaluate this by, again, because this is a Lisp capable editor, we use a keystroke. Actually, I'm going to use the menu, and the menu says incremental evaluation right there. So we see over in the debug window, it gives the name of the function we define, and let's just try and call it here, and that is the current universal time. And let me just so decode universal time. Let's try that. There we go. The variable star is always set to the last evaluation done. So that's set to the result of the previous evaluation, which is that universal time. And, oh, just like that. I'm sorry, I did the wrong thing. That thing, format returns nil. So what was returned there is nil, which is not a universal time. But let me just show you this function anyway, and we'll just grab the value there. So let's see what this is telling us. It's we're in, at least, I'm in time zone 8 in California. Daylight savings time still applies. It's the year 2010. I forget what that number is. It's the month 9, which is September. It's the 8th day of September. It's currently 10 hours, 10 o'clock, and 9 minutes and 33 seconds. So just introducing you to that function. We're not going to go into that in more detail. Anyway, so you're working with an editor. You write code. You evaluate it in the read eval print window or in the editor, as we did there. You bring code in the Lisp world by entering it directly, typing it directly to a prompt, or by loading it from editors or files. And code loaded into Lisp may be interpreted or compiled before loading. Definitions written in Common Lisp can be compiled. The compiler can be applied to a file or to a single definition. So when you compile a source file, which typically has the extension CL, you create a compiled Lisp file, which typically has the extension FASL, F-A-S-L, stands for fast loading, but it's not important. You can load a source file, in which case it will be loaded and will be run interpreted. You can compile it and then load the corresponding FASL file. And just keep these things in mind. Compiling a file does not load it into the Lisp session. Typing a definition directly to the prompt does not create compiled code. You have to compile the functions you type there, or compile the file and load the compiled file. And incremental compilation means that you compile the designated code and load the newly compiled definitions as you're going. If you're using the editor, you can use keystrokes or menu items to compile and load definitions. And just a word about applications. There were a couple of slides on this last time that I didn't cover, but if there are any questions on them, please ask. If you are working with someone who also has a copy of Allegro CL on the same platform, or typically on any platform unless you're using platform-specific details, you can share the source code, they can compile it and run it. If you can also supply them with compiled files, and you can also produce standalone applications which should be given to anyone with the same operating system, and standalone applications do require that you be licensed to provide to distribute those. Now we're getting into actual Lisp definitions. That was mostly review, and we're going to start out by talking about the format function. Format is a function. It takes two required arguments and then as many additional arguments as necessary. The first required argument, which I was trying to highlight, but that doesn't work on slides like this. The first required argument is telling the system where you want the output printed. It can either be the symbol T, which means print it to the Lisp listener, or it can be the symbol nil, which means don't print it anywhere but create a string and return the string, or it can be a stream. And a stream could, for example, be a open to a file, or it could be any of a number of predefined streams. But typically, in the examples we'll be using, we'll either say T, meaning write it to the standard output, which is the Lisp listener, or nil, which means create a string. Now, the second argument is a string, and that's the string that's going to be printed out. In this case, it's just a plain string with nothing, which are called control characters. So format simply prints that string. Hi, I'm David, right there. And then returns the value nil. This isn't a value that it's evaluated. This is it doing its work as a function. The return value, format, typically returns nil unless its first argument is itself nil, in which case it returns a string. Now, in this second case, we have format T, and there are these various characters preceded by a tilde. And so we have tilde%, then the word hi, comma, I'm, tilde A. Now, tilde% means put in a new line. Here's the new line. Notice here it started at the beginning of a new line, but there's no blank line above. Tilde% says put in a blank line, and that's what it did. Tilde A says read the next argument as a Lisp object and print it as a Lisp object, and that's what it did here. This is the symbol David. Remember, in the Lisp we're running, this is upcased, so it's all caps David, and it prints it out exactly like that. Finally, here's the same control string with the same just one control character, tilde A, and otherwise the same, but we have format nil, and that means it's going to create a string. This is the easiest and quickest way to create strings. There is a function called makeString, but if you know what you want to create, using format's the fastest way to do it. And if you remember back, excuse me, in the example I ran here, where I was trying to construct the symbol name, and where was I doing that? Up here. And I was doing find symbol, which takes a string and finds the symbol with that string as its name. I converted the numerical argument that was passed in into a string using format nil. And then tilde D means print a decimal number, and the num argument was either 1 or 2 decimal numbers. So here's a more complicated format statement where, again, we're printing to the listener or the terminal, and we put in a blank line. We say the circumference of the circle with, now here's a tilde with a return and lots of spaces. And when it's printed out, you notice that that tilde and all the spaces are ignored. In other words, as if we typed with space, radius, tilde d, etc. The reason for having this tilde followed by a return and then any number of spaces is to allow you not to have to put everything on one line, and so to make your code more readable, but still have the result be formatted the way you want. So this just simply says ignore the return which follows and all the spaces until you see something which is not a space. Notice we put the space after with in before we type the tilde, so it appears right there. We're saying the circumference of the circle with radius tilde d means print a decimal, is tilde percent means another new line, tilde f means print a floating point number. Radius is going to be a decimal, it's 14, and 2, pi is a constant with the value pi, and radius, that's how you get the circumference of the circle. And we also do format t, another new line. The area of the circle is another floating point number, and this is the formula for the area of the circle, and this is what prints out. The circumference of the circle with radius 14 is 87.96, etc. This is a double float. The area of the circle, the area of that circle is 615 and change. So there are lots of format control arguments. Tilde A prints any Lisp object. Tilde S prints any Lisp object. The difference between those two strings are quotes are suppressed in tilde A and included in tilde S, so it's whichever you want. Tilde D prints a decimal integer. Tilde F prints a float. Tilde percent prints a new line. Tilde return says ignore all the spaces. Here's another example. Now, there's another thing about these format control characters. The tilde begins the control character, the letter and certain non-alphabetic symbols, ends the control character, and there can be additional arguments in between. So the 5 in tilde 5f says use 5 spaces for printing this value, this floating point number. And the result, as you see in the next line, is we're printing pi, and it is 3.142. That's 5 spaces, 3.142. If we did 6, it would be 3.1415. It's rounded up, you notice, or it's rounded this value because it's only printing 3 decimal places. So I think we're beyond, yes, that's the last of format, but what I want to show you is, let's go down to here. Now, let me just type a format statement here. Tilde 7f and pi again, just to show you. So it's 3.1415. But let's look at the description of format. And if you hit F1 when the cursor is on a function name, it will bring up the documentation, which just takes a second there. So here is the ANSI spec documentation of format, and what I wanted to control string of format control, and I was Oh yeah, so we go to section 23. For details of the control string, you go to this section, formatted output, and let's just, this button says go to the next page, and here you see it's starting to list the various, so tilde-C says you're going to print a character, and here's an example. So format nil tilde-C, that's the representation of a character, capital A, prints it as a string. Here it's printing a space. Tilde percent's a new line, tilde ampersand is a fresh line, which means put in a new line if it's needed, otherwise don't. Vertical bar says a new page, and you just sort of scroll through these. And what I wanted to say is that many of these have examples. Not this one, unfortunately. We go to some more. They're telling you what anyway, what everybody does when they're doing format, you don't remember all of these various command characters. You just go to the documentation and you look for something that looks like what you want to do, and then you kind of copy it. These tilde A, tilde S, tilde D, tilde F, tilde percent, and tilde return are ones that are used all the time, and you should probably remember them. But there are lots more, and nobody remembers all of them. So now we're moving on to conditionals. And if you've done any programming, you know that conditionals are one of the fundamental constructs of programming. Basically, if you want to do a program, I mean, you could have a program that just does a bunch of instructions and then stops. But if you want anything that's at all complicated, at various points you have to decide whether you're going to go one way in the code or another way in the code, and you do that with conditionals. And there are a lot of built-in conditionals within Lisp. The elementary one is called if, which we're about to look at, and then there's also when, unless, and then several multiple possibility conditionals, cond, case, and e-case, which is a special example of case. Now, most of these, as I will point out, could be constructed out of if statements, but they have sort of make for more readable code, as we will see. But let's look at the if conditional. The if conditional, if takes two required arguments, the test form and the then form, and one optional argument. It's not specified as optional there, but it is. When you evaluate an if form, it evaluates the test form, and the test form will either return nil, which means false, or will return any other Lisp value, any non-nil Lisp value. It doesn't have to be the symbol T, which stands for true. It can be any value, so long as it's not nil. That is, in Lisp, nil means false, and everything else means true. So any non-nil value from the test form means the test form came out true. If the test form comes out true, the then form is evaluated. Otherwise, nil is returned if there is no else form, or the else form is evaluated if there is an else form. So for example, here's an if construct. We need these are variables, and they have to have values. We haven't defined them, but we presume they're defined. If the value of save symbol is EQL, we'll get to equality statements presently, the value of the variable password, then print pass, otherwise print fail. And just reiterating what I just said, if the test returns non-nil, execute the then part and return its value. else, execute the else part, and the else part is optional. Now there's one fact which is quite important. Only the form, the then form or the else form, whichever one is reached is evaluated, but the other one is not evaluated. And so it's guaranteed not to be evaluated. And let me just show you an example of that. The thing is that if you want to, let's see, I think there is, it's file length. Is there? I never can remember, but yes, there's a function file length, and so we're giving it a file name for a file that doesn't exist, and so there is no file, so it simply returns nil. While what I wanted to show, what's something that would so I said if file length in of no file. There's a function which has slipped my mind at the moment, which will test whether a file is there. But no file length does roughly the same thing. So it says if a file length of no file returns a non-nil value, which means there's a file there and it has a length, then open it, otherwise return nil. Now the point is that the open no file signals an error if it is evaluated, but the thing about an if form, if the test fails, as it does in this case, it doesn't evaluate this at all, so you don't get an error. And that is why that promise that it doesn't evaluate the clause which is not reached is important. Now, so here's just some examples. We have a function called sign name. It takes a number as an argument. If the number is greater than 0, you return positive, the symbol positive, otherwise you return the symbol not positive. Notice that negative would be wrong because 0 is not negative. A Boolean test returns nil or true. This is a Boolean test. And so a typical form is if test, then do this form if true, otherwise do this form if false. And here are just some more examples. And here we have a if statement nested within an if statement. So here we're actually going to do positive, negative, or 0, similar to the one that we just did, which is just positive or not positive. So we have an if statement. If number is greater than 0, return the string positive. If number is not greater than 0, then test if number is equal to 0, return 0. Now, if number is neither greater than 0 nor equal to 0, then we know it's negative, and so we don't have to do another test here. We don't have to test that number is less than 0. We know that has to be true because those are the only 3 possibilities. So here we have a function that will return the strings positive, 0, or negative as the argument is positive in this case, negative in this case, and we don't have 0 as an example, but if we gave it 0 as a value, it would return the string 0. So here we have 2 nested if statements, and you can nest as many if statements as you like in order to go through a whole range of possibilities. Now, one thing about if is that you only get to evaluate one form. So if we go back here, here's the test, and then there's one form if it's true and one form if it's false. If we wanted to do more, if we wanted to do various things, we can use the form Prog, and we can then list as many forms as we want. Prog n just means its arguments are a whole bunch of forms, and you just evaluate them in order and return the value of the last one. So these forms have side effects, so those side effects get done, in this case printing, and so we're saying if this test, 3 bigger than 2, well it is, then evaluate all these forms, and we simply wrap them all in a prog n so they all get done in order. And it prints A, it doesn't print this stuff, that's just a label, the less thans of the printed. It prints B, and then it returns the value of print B, and print returns the thing it printed, so there's B. Now there's also a function prog1, and it returns the value of the first form. So here we have it with prog n, returns value of the last form, we get B. Here's prog1, returns value of the first form, so it returns A. That's what print A returned. The point of this is that you get to choose between whether you want the first value returned or the last value returned. And there's even a prog2 that will return the value of the second form, which every once in a while you actually come up with a use for, but prog1 and prog n are the ones that are most commonly used. Now, there's a special form of when, a special form of if, which basically only has, you only have code if the test is true. If the test is false, you just return nil, that's it. But you only have, and that's when the test form, and then as many result forms as you like. So this is, in fact, more or less equivalent to if test prog n, form 1, form 2, form 3, etc. And it's just an easier way to write it. You don't have to put in the prog n is put in automatically. So we're saying if save symbol is equal to the password, then open the vault and record the contents and close the vault, etc. All these functions, of course, you have to have defined, just as you have to have given values to those variables, and multiple body forms. So it's just it's actually a macro, and it's basically, if we macro expanded, it would probably look something like if test prog n, the various codes there. There's also unless, and it does the test and only executes code if the test returns nil. So this is basically a simplified form of if if not the test, if the test is untrue, prog n a bunch of forms. You can have as many forms as you like. We only have one here, call the police, but we could also have ring the alarm, etc., etc. So again, this is equivalent to when not the test, then do as much code as you like. There are additional tests, not simply returns when the next form is true, it returns nil, and when the next form is nil, it returns t. So a not form always returns nil or t, and it's the opposite of what the form evaluates to. And evaluates the forms one at a time until it reaches one of them that returns nil. If none of them returns nil, it gets to the last form. It returns the value of the last form. Or evaluates the forms one at a time until it finds one that returns true. Otherwise, and as soon as it finds one that returns true, it returns the value of that form. And now, and or, just like if, will stop evaluation at the point that when AND will stop evaluation when it reaches the first form that returns nil, or will stop evaluation when it reaches the first form that returns true. And this, again, is important, and let's go back to my example here, and we can do it with AND, if I could spell. Returns nil because no file doesn't exist, and therefore its file length is nil. And so it never, AND evaluated that, it returned nil, the evaluation stopped. It did not evaluate the open, because if it had evaluated the open, it would have signaled an error. So this is part of the guarantee of AND, that it does not evaluate the forms beyond the first one that returns nil. Similarly, OR does not evaluate forms beyond the first one that returns true. Now, just for the kinds of tests that you do, they're numerical comparisons, greater than equal to, less than or equal to. There are objects being EQ, meaning they are absolutely the same object. EQL, which means they are the same object or the same integer or the same, character. EQUAL, which would be or the same strings. You can look all of these values up. Let's just go back here. So symbols are EQ to themselves. But strings are not EQ to themselves. I mean, to their strings which are the same are typically not EQ. In some cases they might be if they're referring to a stored string which is stored somewhere for efficiency's sake. But in general, you will find that strings are not EQ to themselves. Now, numbers like 2 in Allegro CL are EQ to themselves, but that's not a requirement. There could be another Lisp implementation where integers like 2 are not EQ. Integers are always, or small integers, fixed nums, are always EQL and the same. Let's try a big num. I actually don't remember. I don't think big nums are. So a big num is just something with lots of zeros. And let's just copy that. Notice the indentation there. And I don't think they're EQ. No, these are big nums, which means they're stored. The largest fixed num is that number. The difference between a fixed num and a big num, we're not going to go into this in great detail today, but the difference is that a fixed num is stored very efficiently in a single word in memory, while a big num is stored as a much more complicated object. But a big num Lisp can handle integers of essentially any length. I mean, that obviously eventually you overflow things, but you can easily have integers of 10,000 digits long. But using them is quite space intensive. Fixed nums are just incredibly efficient to use. So 2 fixed nums in Allegro CL are EQ. So let's see whether these are EQL. I don't actually remember whether they would be. So let me try and do this. There we go. We're going to put an L in there. And the answer is yes. So 2 numbers or 2 integers are EQL. Integers, the same integer, are always EQL, even though they may not be EQ. Strings are not EQ, and I think probably not EQL. So let's just try that. And the answer is no, but I think they are EQ UAL. Yes. One keeps in mind which these various definitions. There's another one too, by the way, called EQUALP, and I think in that case strings that have the same letters but not necessarily the same case are equal P. But in any case, EQ is easy to remember, the same object. EQL is the same object or characters, the same characters or the same integers. EQUAL is a more general notion of sameness, the same strings, etc. But you don't necessarily remember all of these things. You check the documentation when you're using them. There are additional specialized. Here's equality of numbers is the equal sign, and equality of strings. There are two functions: string with an equal sign and string hyphen the word, EQUAL. The first one is case sensitive. The second one is case insensitive. So radar, capital R, ADAR, is string hyphen EQUAL to all caps radar, but it's not string equal sign. Then also every object in Lisp has a type. Notice with a function we're evaluating the variable x, so we're looking at the value of x. We're not asking whether this symbol is an integer. It isn't, but its value, we're asking whether the type of its value is an integer. And so you do tests on values, and you ask what their type is, and you see whether their type is of a particular predefined type. Now, here are some compound conditionals. And you remember just a few slides ago, we had a compound if statement, and where did I put it? There we go. We were trying to determine whether a number was greater than 0 and positive, or equal to 0, and therefore 0, or the third possibility less than 0, and therefore negative. And we had these nested if statements. And if you have a lot more possibilities, you end up with a tremendous number of nested if statements, which gets very confusing after a while. So there are predefined tests like cond, which simply is short for conditional, which is a series of tests and has a format that is easier to read. It isn't a series of nested if statements. So the format of a cond statement is its arguments are a series of lists. The first list is here, and each list contains a test form and then one or more result forms. So we're saying the test form says if x, which is a variable which has been predefined and has a value, if x equals 1, then do this and return the value of this statement and don't do anything else. If it doesn't equal 1, you go to the next statement, which says if it equals 2, print these, do these two commands, print twin, print you win, return the value of this print statement, and don't do anything else. Here's where x equals 3, and this last case, it's just t. It evaluates that form. Of course, it comes out to t, and therefore the form passes. So this last one is a catch-all form, which will always be true if all the previous ones fail. And so it will then print unknown, print too bad, and return the value of x. And now, this is a typical compound Lisp form, here is where the indentation of a proper Lisp editor is a good thing, because you notice that all the format statements are, all the statements are indented so that they line up correctly, and you can tell what's going on. Let's just do that quickly in the editor. So we're doing cond, and then 2 parentheses equal x1 return print 1 return. Notice that I'm indented, and that's when I notice, oh, I need another return to get through that first clause. Now I'm in the correct position, and so I can do equal x2 print 2, for example, and I'm just closing it off. But I just wanted to show you how the editor is useful for you remembering where you are and making sure you're doing things correctly. So that's cond. There's also, this is just a repeat of cond, and there's another compound conditional called case. So here you have a form which is evaluated, and then so it has a value, say x has the value 3. Then you do cases. The first element of the case is either a single value or a list, and if the value is one of those things, testing with EQL, you do the remaining forms. So if x is 1 or 5, you do this. If it's 2, you do this. If it's 3, 6, or 9, you do that. And then you can have either t or otherwise, and that's what it will do if all the other ones fail. Now, if none of them turn out to be true, here we have case x, it evaluates x. If it's 1, you do that. 2, you do that. 3, you do that. If it isn't any of those things, if it's 7, you just fall through and it returns nil. And just here are some somewhat more complicated examples. And in this one, notice we do case read. And case read means that it's going to prompt the user for input. The user will type input in and hit return. The input will be read. And then if it's yes, the symbol Y, the symbol yes, the symbol T, or the symbol OK, it will offer the counter offer. Otherwise, it will just offer the offer. This is sort of a bidding function here. Here is a more complicated one, and it's demonstrating the predefined function yes or no p. And so it's asking a question, and then you return y or n. Let's just demonstrate that quickly. So y or n, and let's do, so yes or no p, that's b. Do you accept tilde d question mark 22, see if this works, and it does a nice dialogue, and you click yes, and it returns T, and if I clicked no, it would have returned nil. If you're doing this not in the IDE, it won't bring up a nice window, it will just print it, but that's just a predefined function which will ask the question. Now, there is a variant of case called eCase, and then if you fall through, if none of the cases is true, you'll get an error. Typically, you use eCase in when you're initially programming. So you think you have all the possibilities for the value of x, and the possibilities here are 1, 2, 3, and 4, but you think you've included all the possibilities, but if somehow x gets the value 5, when you're running your code, you'll get an error, and that will tell you, oh, it's possible for x to be 5. I should have taken care of that case. You less commonly have eCase in a production application because users always get confused by errors. And so you simply, in a production application, do case with a T or otherwise statement where you say, where you do something, where you handle it. There are ways to handle errors as well, but that's in a more advanced course. Type case is another example. You have, again, it evaluates some variable or some form, and then if that value is an integer, you do this, a single float, you do that, a double float, you do that, and something else, you print dunno. E-type case, again, will signal an error if it falls through. Again, this is more for developing code than for production code. Now we get to iteration and recursion, and we're going to spend most of the rest of the time on this, and then a short bit on program control, and then an introduction to packages. So, iteration means you want to do things a number of times. You specify the number of times, and you specify how you're going to, what you're iterating over. This being Lisp, the list is one of the basic data structures, and there is the macro do list, which iterates over elements of a list. So here we have, we've defined the variable lunch to be the list, apples, oranges, and pears, and the do list form has a iteration variable, which is called element here. It iterates over the list and does the body, which here is just one form, saying to print it for each element of the list, and then it returns the third element of this argument list, which there is no third element, that's optional, so it returns nil. In this case, it returns done because the third element is done. So let me just show that quickly so we can, so I'm just going to A, O, and P. So apple, orange, and pear, I'm just not a fast typer. So it prints A, prints O, prints P, then returns nil. If we had put a value in here, it would return that instead. There you go, done. Do times iterates over a number of consecutive integers. Do times I is the iteration variable, 5 is the upper limit, the lower limit is always 0. With do times, you always start at 0. So so do times I5, print I is going to print 0, 1, 2, 3, 4. This is the same thing we did for do list, except we take the length of the list and iterate over that and print the nth element of the list at each time. It will do exactly the same thing, print apples, oranges, and pears. And remember, the first element of the list is index 0, and index up through 1 less than the length of the list. There's just one thing I want to mention. Suppose that you want to print 1 through 5. So if we do times I5, print I, we get 0 through 4. So if we want to print 1 through 5, you just have to remember there are two ways to do that. Well, there are many ways to do it, but one is that you increment the argument you're printing. There's 1 through 5. Another is that you have a secondary variable defined outside, defined outside the do times form. And again, 1 through 5. Now you're saying, well, why did you do that? Why didn't you just print 1 plus I? And the answer is, in this case, obviously, it's much more efficient to print 1 plus I. But if you have a much more complicated body where you're using the variable incremented by 1 many times, it's rather tiresome to keep adding 1 to it. It's also very inefficient. So you would create the secondary variable, set it to 1 plus the iteration variable, and then use the secondary variable from then on when you wanted 1 plus the variable. So do times is the return value. We've shown this. If you put a third element to the specification here, that's what gets returned, has no other effect. Now, the do macro is a very general iteration macro, and it takes some getting used to, but once you've learned how to use it, it is incredibly powerful. So the thing is that it has 3 constructs. The first thing is the set of initialization binding forms, creating variables. So we have the variable I, its initial value, and then the form which is evaluated each time through the loop. So I starts at 0, and the next time through the loop, it is set to this value. This value is, in other words, I is incremented by 2 each time. J starts at 7, and each time subsequently through the loop, it's incremented by 0.5. This goes on until I and J added together. So the second thing here, the first 2 lines of the binding forms and initialization forms. Then there is a list, which is the test for when you should stop, and the return value. Done. And then there is the body. And the body here is 2 forms, print I and terpre, which means print a blank line, print a new line. And so this will go through. We'll start I at 0, J at 7. 0 plus 7 is not bigger than 50, so you're not done. Print 0 and print a new line. Then I is set to 2, I plus 2, 0 plus 2. J is set to 7.5, current value 7 plus 0.5. 7.5 plus 2 is not bigger than 50, so you're not done. You print I, which is 2, and it continues doing this until, I don't know, let's see, 20 odd times, no, probably 16 or say odd times until that value is actually bigger than 50, at which case the body is not run and you're done. So again, here are the syntax, variable, the initialization form, the step form. The step form is optional. If you leave it out, the variable keeps the initial value forever. Then an end test, a result, and the body. it's very, if you think about it, you could implement either do times or do list using do. Now, here is another iteration operator called loop, and loop has two formats. One, it's without keywords, and loop without keywords simply iterates its body forever. And no, generally you don't want something iterated forever. And the way you get out of a loop, which is iterating for forever, is that when it sees a return statement, that's open parenthesis, return, close parenthesis, it jumps out of the loop, returning. This will take arguments, will return whatever argument you give it there. Here we gave it no argument, so it's going to return nil, but it will just go through that loop. So I is started with the value 0. So you're looping. It's saying, is I bigger than 10? No. So then you increment I and you print it, and then you go through the loop again. I is now 1. Is it bigger than 10? No. Then you increment it and print it. It's now 2. Then it's 3, 4, 5, 6, 7, 8, 9, 10. And when it gets to be 11, I is bigger than 10, and it returns. So this is loop without keywords. And if we go back, so in fact, in this, the program that's running this debug window is in fact just in a loop statement like that. And it's saying read input, evaluate the input, print the result, print a prompt. And it's just doing that over and over again. And the way that you get out of this is that you actually exit Lisp, which will cause a non-local exit, and that will be that. Now, there's also loop with keywords, and you have to look in the manual for examples of this. Some people love loop and use it for everything with keywords. Other people, and I'm one of them, don't care for it. But basically, the keywords here are for, from, to, collect. And it reads more like an English sentence. Loop for I, that's the iteration variable, from 1 to 7, and collect I squared. And there you go. The result is collect means bundle up in a list in order. And so 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, through 7 squared. Notice that we say 1 to 7. It actually goes 1 through 7. Doesn't go 0 through 6, which is what do times would do. So it's much more explicit. Loop for j from 0 to 3 by halves and sum j. So it's 0 plus a half plus 1 plus 1 1/2 plus 2 plus 2 1/2 plus 3, which according to this is 10.5, and I assume that's correct. So there are many options. There's lots of power. You can collect, which means bundle up into a list. You can sum, which means add. You can maximize, which means get the largest value. Minimize means get the smallest value. A whole bunch of other things you can do. We're not going to go into it in much more detail. One of the problems with loop is that sometimes it's very difficult to figure out what's being intended, and sometimes it's easy to program incorrectly without realizing it. So we just basically want to tell you that it's there. Some people learn it and like to use it, others not so much. Here's just a couple of examples. We loop from num for num, the iteration variable, from start num, the first argument, to end num, the second argument. Do means simply evaluate the following forms. There you go. My count 1 to 4. If we'd done this with do times, we would have had to have added 1 to the iteration variable because it would have gone from 0 to 3. So you can use do times, and do list to achieve the programming tasks that loop with keywords. You can write code to collect, sum, maximize, and here's sum. We're defining a function, takes a list. We start out by binding a variable to 0. We go through the list and we set that variable to itself plus the item. So we add 1, 2, 3, 4, and we get 10 as a result. Here's how you find a maximum. You start with something which is the first element of the list, and then you iterate through the rest of the list. You could actually iterate through the whole list, wouldn't make much difference, but it would be slightly inefficient because you already have result being the first element of the list. So you go through every element of the list. Is it bigger than the current result? If it is, set the result to it. Otherwise, do nothing, and then return the result. Here we get 1, 2, 3, 4. We get 4, but if it was 4, 3, 2, 1, we'd also get 4. Excuse me. Here's just another example where you are using conditionals to do something with the item or not, depending on, in this case, whether it's even. So it's going to print 10, 2, 4, and 8, but it won't print 1 and 7. Now we get to recursion. Recursion is a particular Lispy, which is a nice technical term, way to do programming. And recursion is a special kind of iteration in which you define a function which calls itself. Now, this isn't supported in many languages, but it is supported in Lisp. A recursive function will terminate. You have to have some termination condition, but in the course of doing its work, it calls itself, and it has to call itself with different arguments. If it calls itself with the same arguments that it called itself with before, generally you'll find yourself in an infinite loop. And we'll see an example of this in a second. So here is a recursive function. We define the function find even, and it takes a list as an argument. And we then let item be the first element of the list, and if item, the first element of this item, is a number and it's even, we return it. We're done. But if it's either not a number or it's not even, we simply call the function find even, the function we're just defining, again. On the list, rest means cut off the first element of the list and call it with the remainder. And let's just go off and try this, and we're going to define this over here. So remind me what the, so what are we doing here? So we're calling it find even of list. Good, I can remember that. So we start out with the first element of the list. And if, and we check whether it's a number, and we check whether it's even, and if both of those things are true, the if form will return the item. Otherwise, we call find even of the list less the first element. And I'm just going to add something here. I'm just going to put in some print statements. Put in a print statement there, and I'm going to put in a print statement. Notice I'm using Prog N because I want to do two things. Let's see, where are we? Yeah, let's put in a print statement here. And a new line, and let's put in a new line here, and let's not worry about that one. So what are we doing here? We need to close off the Prog N. Nope. I guess we're okay. So there's the if statement, there's the let statement, there's the defun. Let's do a evaluation, incremental compile. So let's see. So we start with the list being 1, 2, 3, 4. It goes through, and the first element is number, but it's not even, so we do find even on rest of list. That's 2, 3, 4. More 2, 2. And notice we don't even have to have numbers. Let's see, quote, A, 3, 4, 5. The A was not a number, so it fell through right away. 3 was not even. We got to 4. 4 is returned. Okay, there's a cute little warning down here. What if no evens? Well, that's an interesting question. So let's try it. So here's one with no evens. Oops, it's just doing nils. And nils, 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 nils. So one thing I wanted to show you, there's a pause break button on your keyboard, and you hit that, and you can get it to break into a program. When you're got in an infinite loop, and then you just hit cancel, and you get your prompt back, and it broke out of the function that was in the infinite loop. Anyway, what happened? Well, we had let's go back where I can show you what I did, and we can come down, and so that's what we evaluated, find even of 1, 3, 5, 7, 9. Well, 1, they're all numbers, but not even, not even, not even, not even, not even. And then we ran out of list. And the value of the list when we called find even of the rest of the list by the time we got to the end of it was nil. When you give nil as an argument to this, the first item is nil, as it happens, first applied, just to give myself a new prompt here. That's nil. So item was nil. It's not a number, so we try find even on rest. Rest of nil is nil. So we just get nil, nil, nil. Remember I said in recursion, you always have to call the recursing function with new arguments. If you call it with the same argument, you'll end up in an infinite loop, and that's what we did. So it's very important that you consider all possible cases, and both of these cases had an even in it, well, just this one, and by the way, this slide is showing trace, and I could have done that and you would have seen the calls to find even, but instead I just put in print statements. But find even, but if you did it without an even number, it would have gone into an infinite loop. here's what the trace output looks like. It's very similar to what my output looked like. It's calling it with shorter and shorter lists, lopping off the first element until it reaches an even number. So here's a fix for that. To find even of list, and you test if list, then do all of that. And let's just modify my function to, we're just going to and we get another thing here. Now we've messed up the indentation. If you come up to the edit window and it says re-indent, you can get the things to re-indent. So if list, and then do this form, and we're going to evaluate that, incrementing this to incremental compile, and now let's try this one again. It runs out, it returns nil, it doesn't go into an infinite loop. Find even, let's see, where are we? Yes, so if list, that's testing whether we have nil. First you see if you're done. If not, you call it with a different argument list. That's the basic thing. Another well-known recursive function, which is factorial. You define the factorial. Remember, the factorial of a number, of an integer, is that integer multiplied by all integers smaller than it down to 1. So factorial of n, if n's less than 2, you just return n. If not, you call the same function with a different list. You multiply factorial of n minus 1 times n. And factorial of 4 calls factorial of 3, calls factorial of 2, calls factorial of 1, which returns 1, which returns 2, which returns 6, which returns 24. Factorial of 4 is 24. List 2 are data structures which are suitable for recursion. Here's a copy list, and if it's not a list, I'm sorry, if it's a nil, that's what not list means. If list is nil, that returns true. Or if it's not a list, list P tests whether its argument is of type list. If it were a number, for example, that would fail. Then just return the list. Otherwise, cons means create a list made up of these two elements. Cons, my copy list of the first element, and my copy list of the rest. So we're applying this to the list 5, 6, 7, 8. So it is not empty list, it's not nil, and it is a list. So we build a list out of the first element, 5, and my copy list applied to the rest. So we're building a list of the first element and a list built of the rest of the list. And if you work this out, you'll eventually end up with a copy of the list. Just a couple more recursive functions. You can get these when you look at the slides. I don't want to go into them in much detail, but what I want to tell you is this first one simply adds up the number, it adds up all the elements of the list. And the second one slightly no, rest of them first. So that's just 2 ways of doing that. But I wanted to show you the third way here, which is where you add, where it's adding up all the elements of the list that are numbers and identifying the elements of the list, which are themselves lists of numbers, and breaking them down. So, yes, this is the example I wanted. This is number 6. So you what this is, and so this will work on an example like this, which is a list that has 3 elements. The first one's a list of 3 numbers. The second one's a number. The third one's a list of 3 numbers. And so the first element, you take the first element. If it's nil, then it's 0. If it returns 0. If it's a number, it adds it to the first element. It adds the first element to the sum of the rest. And otherwise, which means in this case it's a list, you add the sum EM6 of the first element. In other words, you add all the elements of this sublist to the sum of the rest, which is 7 and 4, 5, 6. This is a little confusing, but you should look at this example and work it out. And it will not only do things where the elements of the list are themselves lists of numbers, but it will go as deep as you want. So it will work perfectly well on lists of numbers that, I think it's how it works now, lists of numbers that, where the lists go as deep as you want. Now, that's it for recursion. You should try out those examples and particularly look at the last summing example there, because that's a fine and rather complicated but example of recursion at work. And now we're going to handle non-local exits. So basically you're evaluating forms, and for some reason you want to jump somewhere else in your program. You do that using a non-local exit. A non-local exit is a return to the caller from the middle of some construct rather than the end. The operators that apply to this are return, which we've already run into in the loop construct, and we'll see it again here. Return from and block, which sets up a named context which you can return from, and also the catch and throw, which are basically go-to constructs. Well, they're all basically go-to constructs, as this next slide points out. Return from is a lot like go-to, and it needs some kind of tag or name to give you a something to return from. So let's look at this function. It takes a single argument called item. It sets up a local variable called result and gives it the value nil. Then it sets up a block, and the block goes from this opening parenthesis down to here. Anytime all these forms within this block can see the tag called search, and if you say return from search, it will jump outside of this block and so basically jump to the location which is just after this closing parenthesis. So in here we are doing a list, we're doing a do list where we have some global variable called objects, and we're going through them. We need to define the function match P, but just consider it to be EQL or something. If we find a match, we set the result, the variable result, to that object, and then we return out of this list and out of the entire block. And then we print the result, and we're done. If result is nil, if we get through the whole list, if we go through all of objects and we don't find a match, then result will be nil, and that's what will be printed, nil. Notice that if item is itself nil, and nil is one of the objects in the list object, then there's no way for us to tell the difference between not finding nil in objects and finding it, because nil is returned or printed in either case. So you always have to worry about that. It doesn't affect us if we know that objects is a list of symbols other than nil. It's a list of numbers. It's a list of strings. As long as we know that nil isn't one of the items on this list, we're not going to be confused. But if nil is possibly an item on this list, you have to do something else, and I'll discuss what you might do in a minute. But let's go on with this. So here is a second version of this. Again, you have an item, you have result nil, you go through a list of objects, and here you return from try2. Now what's try2? Well, try2 is the function name, and whenever you define a function, when the function is executed, it automatically sets up a block whose name is the function name, try2 in this case. So here you get, it's not only returning out of this list, it's returning from the entire function. And the difference here is that, therefore, this print statement is never reached unless there is a match. Now, this one, it's a Q result object. Yes, this one's interesting because if let's see, this is, so if there's a match, it sets result to object and then returns from the entire function. The return from the entire function means that the value of result is lost. So what this function will do is that if it finds a match, it will return nil, and if it doesn't find a match, it will print nil and return nil. So you'll actually able to distinguish between finding item and not finding item, but you won't be able to tell which object in this list the item was. So this first case was a useful function, except it was unable to distinguish between finding item when item was nil and not finding item when item was nil. In other words, nil not being there and nil being there. It couldn't distinguish between those two cases. The second case actually distinguishes those two cases, but doesn't actually tell you what object matched. We don't know what match P is, by the way. Obviously, if it's just, these are numbers and it's just equals, if item is 2, then you know it found 2. But if match P is something more forgiving, such as it just simply wanted to match, find an even number or an odd number, then you won't know what even number or odd number it found in this second example. The correct thing to do is return from search here and return a list of the object and let's see, set req. What are we doing here? When match P item set result item and return from search nil and print result. What you should return is something more complicated that tells you that the object was found and So block establishes a named context. Name is a symbol, could even be the symbol nil. The normal return value is the last form of the block. Return from allows an early return. Second argument is the value to return. So return from a block named nil, do times, do list, and loop all establish a block named nil that surrounds them. So here we have our looking for item again, and we do list objects when match p item object return object. And when it gets to the end, it returns nil, which is the value of the third item of the do list. So here it looks for a match, and if there's a match, it immediately returns it. Now, if I have a few minutes at the end, I'll come back to this and show you some of these examples, but I want to get through the rest of the slides. So actually, here's another example. So here we have how many. There are that many objects in the list. Index 0. Here we have a do star form. Do star just means that in these binding forms, the later bindings can depend on the earlier ones, similar to let and let star, do and do star. So we're having four iteration variables. How many, index, object, and match found. And how many is it doesn't change, it's simply the length of objects. That's the number of objects. Objects, remember, is a global variable whose value is a list. Index starts at 0 and then incremented by 1 each time through. Object starts as the nth item of the list object, and each time through is sent to the index item from object. So it starts as the first, that is index 0 item, then the index 1 item, which is the second, index 2 item, etc. In other words, it runs through the list. Match found starts as nil and is not modified thereafter, but can be modified within the text, within the body or the end test. Here's the end test. Or match found, match p item object, in which case match found is set to whatever non-nil value that is. If this is a nil value, it doesn't change the value, it's already nil. And also will stop iterating. So it stops whenever a match is found or index is longer than the list of objects. And it returns match found. There's no body here. This is the test, the exit test. This is the return value. Notice there's no body. We don't need a body. Each time we just run the end test, and it calls match p of item and object. And if it so this will return match found if as soon as match p item object returns true, match found will return. It will return this value. This way, by the way, we know again that a match was found, but we don't know what the item was that found the object. Now, catch and throw, these are somewhat, this is a little complicated, a little hard to figure out. A catch simply sets up a tag somewhere, and when you throw to that tag, it will jump there and evaluate this. It will it will continue the evaluation of this code. Let me put it like that. So we're defining a function alpha. It takes 2 arguments. If the first argument's less than the second argument, then you throw to the tag spaghetti. So then we define a function, recorded average, score, handicap, 3 arguments, and we add the score and the handicap, and we, in other words here, is the score plus handicap less than or equal to the recorded average? And if the score plus handicap is less than or equal to, we throw to spaghetti. Otherwise, we return terrific. So when, let's see, so recorded average is 100, 90 plus 20. I guess this isn't golf because you like higher scores. So the recorded average is less than the sum of score and, let's see, this score plus handicap, I'm just getting confused here. Recorded average is 100, and yes, if the first argument is less than the second argument, you throw to spaghetti. So score plus handicap is less than the recorded average, you throw to spaghetti. Otherwise, you return terrific. So in this case, the recorded average in both cases is 100. 90 plus 20 is 110. That's bigger than 100, so you return terrific. That 70 plus 20 is less than 100, so you throw out of this form here. In other words, throwing to spaghetti means that you drop out of this catch form, and that means you return nil. So here's another example, and let me run through this function quickly. Catch test is the name of the function, takes a single argument n, and typically indicates an integer. So here we have catch location. Then we print before thrower call and print a new line. Then we call the function thrower. Then we print after thrower call and another new line. And here's after the catch frame. And so if n's bigger than 5, we throw to location. Otherwise, we drop through. And I hope when thrower throws to location, forms after the call to thrower and the catch frame are not executed. So in catch test 10, the thrower will throw. The throw is in this form thrower n. So we evaluate this print form and print before thrower call. Then we evaluate the new line. Then we call the thrower function. If it does not throw, we then print after thrower call and another new line. And then we drop down to after catch frame. So in the case of 10, is 10 bigger than 5? Yes, it is. So we do the throw. So before thrower call and after catch frame, but we don't see after thrower call. 0, less than 5. Thrower won't throw. Before thrower call, after thrower call, then we drop down to after the catch frame. So that is basically catch and throw. These aren't ones that necessarily come up in programming very often. Typically when you're doing user interfaces or something like that, if you go into the debugger in this, what was I doing? I was doing open. This is what got me. Well, let me just get an ordinary error, like evaluating a variable that doesn't have a value. And I just say cancel. What's likely going on within the program, which in the part of the program which is maintaining this window and printing the prompts and so on, is that when I hit cancel, it just did a throw to the top level and says to the code which says just print the next prompt. So that's the kind of place that you typically use catch and throw. You can easily do a lot of Lisp programming and not do catch and throw, but it's important that you're aware that they exist. thrower will throw, let's see, oh, that was just the example that we ran. And usually the tag of a catch is typically a symbol, and it's a bad idea for it to be a number. It establishes what's called a catch block with the name of that argument. The first argument to throw is the catch tag, and the second is the value to return. And it doesn't need to be done within the lexical scope of catch. That means the point of that is that the lexical scope is what's in the body of this function down. So you call out to another function. If you remember way back, it won't see local variables unless they're declared special that are set up here, but it does see these locations. In other words, this catch location is seen even by functions which are called by catch test. That's what it means, that it doesn't have to be in the lexical scope. Okay, we're going to, I think this is the last topic of today, which is an introduction to packages. And a Lisp package is a namespace for related functionality, and it establishes a mapping from names to symbols. Packages only refers to symbols. Only symbols can be in packages. Only symbols have packages. Packages contain symbols. There is always a current package, which is the value of the common Lisp symbol star package star. A symbol in the current package can be referenced by name. A symbol accessible in the current package can be referenced by its name. A symbol accessible in the current package is referenced by its name. A symbol not accessible can be referenced by prefixing a package qualifier to its name. And the common Lisp symbol star package star is in the common Lisp package and can be referenced with common Lisp :package or CL :package. So what do we mean by this? So let's just give some examples. Symbols, remember, are, here is the common Lisp symbol which defines a function list. So if we do, I was going to do control, let's do describe. I think that's, if I can find describe, view. I should have found this one before, but all right, well, so anyway, let's do it the old-fashioned way. Let's describe the symbol list, and I have to do an open parenthesis there, sorry. So that tells us about the symbol list, and always prints all of this annoying information, so you have to scroll up. It says, list is a tenured symbol, it is unbound, and it is external in the common Lisp package. And since it's external, and since the current package, which is Common Graphics User, uses the common Lisp package, we can refer to list without a package qualifying symbol. Ignore all of those. Those are all the packages that are accessible at. It has a function binding, etc. Describes this useful function that tells you about any Lisp object, in this case a symbol. But there's a function defforeign, where you can define, and let us do control period, and that will complete that symbol. And you notice that their defforeign, the symbol defforeign, is in the foreign functions package, and it's in the foreign. Defforeign is a tenured symbol, unbound, external in the foreign function package, and accessible in a whole bunch of packages, but not in Common Graphics User. Therefore, in order to reference that symbol when I'm in the current package's Common Graphics User, I have to provide a package qualifier that tells the system what package to look at. So foreign functions, def foreign. So I'm going to show you a couple of things about this in a second, but let's go back to the slides and notice you can always package qualify a symbol, and then its meaning it's unambiguous. And if the symbol is accessible, you don't have to package qualify. The point is that you are trying to type names, and there are various namespaces. Two of you are working on the same application. You might use the same symbols, and these will conflict unless you each have your own package and define your symbols in those packages. Then they won't conflict, because one of the symbols, say my symbol, will be in your package, my package 1, the other user, my other user as the name of the other package, my symbol will be also in that package, but each one, the two namespaces don't collide because they're maintained in different packages. And if a current package is in package A and package A uses package B, then exported symbols of package B, it should have the word exported there, do not need package qualifiers. Packages generally use the Common Lisp package, so symbols in the Common Lisp package typically do not have to be qualified. Common Lisp implementations always have these three packages, but in fact have a lot more. The keyword package is for symbols used as markers. The keyword symbols always evaluate to themselves, cannot have another value. They don't typically have functions defined on them, but they can. And they're printed with a leading colon, but nothing else before the symbol's name. From n, colon from test. They always evaluate to themselves. What does that mean? We come here, if we type the keyword foo, it evaluates, in Allegro CL, we actually reserve the colon symbol. There's no point in typing a keyword because, gosh, it evaluates to itself. So we've actually stolen the colon key, the colon prefix, and made it a top-level command character. But that's just Allegro CL. The initial value of package is Common Lisp User in general Allegro CL and Common Graphics User in the IDE. The Common Lisp User package uses Common Lisp and also the EXCL package. Common Graphics User uses Common Lisp, EXCL, and the various Common Graphics packages. So here's just this value of package when this, if you're just running Lisp, not in the IDE, it's a Common Lisp User package. It has nicknames, CL User and User. You use find package on a keyword to get the package object. This is a package object. It's not a symbol. The package name of this is Common Lisp User. It uses the Common Lisp package and the Excel package, etc. Here is what's true in the IDE. This is what we'd see. Common Graphics User uses all of these packages, also IDE, slightly out of date. Now, you define a new package with def package, and so you just give it a name. You can use strings, but we recommend using keywords. So that creates my first package. It, by default, uses the Common Lisp User package, so since we didn't specify packages to use, it automatically used the Common Lisp User package. When we switch into that package, notice the prompt will change, and any symbol we create will be in that package. So my function is in my first package. It's not in user or any common graphics user. So my function is a symbol internal in my first package. Now we go back to the common graphics package. In order to call this function, we have to package qualify it, and we have to use a double colon because it's internal. We could export it, and then we would only need one colon, but until we export it, we'll need two colons and the name my first package. Every symbol is in a package. It's either internal symbol of that package or an external symbol. It can always, internal or external, be referenced with double colons. If it's external, it can also be referenced with a single colon between the package name and the symbol name. An external symbol, part of the package's public interface, exported from the package, can be referenced with a single colon. But double colons always work. When you have a file of Lisp code, you should start out with an in-package form that says what the package should be when that file is compiled or loaded. And typically, you only have one such call, and it appears in the beginning. Applications should typically define their own packages. This prevents conflicts in the way I briefly described before. And that is the end of the slides for this thing. We have just a few minutes. So let me see. Let me just do a little bit of def package, my pack, and use. So what do we want to use? We want to use CL. We want to use EXCL. Excuse me. We want to use Common Graphics, and we want to use the IDE. And that creates my pack. So we do in package. Just to remind you, let me show you what package is. It's the Common Graphics user package, in package, my pack. Notice I'm using keywords for everything, easiest way to do things. Also, it will handle the case. If we were running a modern list, the package names would all be lowercase, but the keywords would themselves be lowercase in that. So everything would work if you use keywords. And so now, it's my pack. Now let's define a function, myFun, takes a single variable and adds 1 to it. And so myFun is 2, is 3, I hope. Yes. Let's go back to CG user. You can do that with the top level command, :PA, and see, that's called a top-level command, and CG user. Whoops, don't need a closing parenthesis. Notice the prompt is now CG user, and if we look at star package star. Now, let's try and call myFun, and I tell you now we're going to get an error, because what's the problem? In this package, myFun doesn't name a symbol, which already exists. It will create a new one, but it doesn't name the symbol that I created up here because I didn't package qualify it. So there are various choices here, and notice that it sees. You know, there's myFun is in the myPack package. Maybe that's what you want to do. But no, I'm just going to so now I'm going to export my, what did I call the thing? myPack, myFun from I'm going to export it. And what's it doing? Inbound variable. I'm sorry, I should have put a quote before that. Right there. Okay. So let's try this again. Still won't work, by the way, but it's going to give me a slightly different error. And it's going to say still, but notice that it's now mypack with a single colon. This means that if I use the package, mypack, the exported symbols will be accessible without package qualifiers, but we're also going to get an error now. And the problem is that when I called myfun without any package qualifiers, it created a symbol in the Common Graphics user package called myfun, because when it sees a symbol, it creates them. And now when I try to use the mypack package, it's saying, wait a minute, myfun, mypack : myfun is conflicting with Common Graphics user : myfun. I don't, you have to tell me which the unqualified name myfun should refer to. So you get this rather slightly confusing error message. Using package mypack results in name calls. The error message is clear. The question is, what do you want to do? And the one choice is unintern the conflicting symbols from the Common Graphics user package. And regardless of whether you understand what that means or not, it's always what you want to do. The thing is that if I type defforeign like that, I've created the symbol defforeign in Common Graphics user. If I now try to use the package, this is much more common, use the package foreign functions, I'll spell it out, well, never mind, I'll just use the nickname, FF, I'll get the same error. This results in conflicts to this symbol. Remember, what you always want to do is the first choice, whether you understand the meaning of the words or not. And now defforeign refers to the correct, let's see, what do I want to do? Describe. And if we scroll up after this annoyingly long message, it says tenured symbol external in the foreign functions package. Okay, that's it for today. Next week, the third and last class. And obviously, if you have any questions, please ask or send email to training@franz.com anytime, and we'll answer you. You can send email to me. I do read my email. Always better to use a general mailing list. Thank you very much.